Hello, welcome to second part on integrals here. We're looking for rules for definite integrals. Please watch the video on what a definite integral is and area under a curve before this one. So here are some properties of definite integrals. Last time we defined a definite integral as an integral with boundaries, basically limits to the integration. So these rules are identical to the rules we already know for indefinite integrals. They behave the same way, but now they just have these boundaries. So for example, we know if there's a constant times a function, we can remove the constant and then take the integral. So that works the same way with these definite integrals. The second rule is when we have an integral, or a definite integral in this case, of two functions either added or subtracted, we can just separate that and do the integral of one of them plus the integral of the other one. So for example, if you had like 2x squared plus 3x, you can just take the integral of each part separately, and that's what this means here. Then we also knew, or we didn't know, this is a new one, when we have the definite integral of a function, but the boundaries are a to a, that is 0. Now think about what that means. Basically, if you remember from the last lesson, when we had boundaries here, for example, we could say x value from 2 to 4 or 0 to 5, and we find the area of a curve or under a curve from those x values. But now, if the two x values, if there's no gap between the x values, then that just means that there is no area that's bounded under a curve because the starting point and the ending point are the same point. So there's no area because you haven't created a shape. Rule number 4. When you have boundaries from a to b and you find that integral, that area is the same as the negative of the reverse boundaries. So think of it this way. If you found the area of a curve or under a curve from 0 to 5, then that would be the same as finding the area from 5 to 0, because that area, that integral, produce a negative value then when you go from a larger value to a smaller value. So therefore, by making that negative, you turn it back into the original. It's like reversing it. And the fifth rule is when you have integration, definite integral of some function from a to b, it's okay to say we have the same integral from a to c and then c to b. What that means is, and we did a few examples like that, when you have an integral over a large area, you can just break it up into separate parts. And that's what this means here. You go from a to some portion in the middle of a and b, and then you start at that point and continue all the way to b to finish. So it's like saying you're going to do an integral or area of part of it, and then continue on and do the next part. And those two parts together will be the full area if you did all the way from a to b. Those rules are important. Make sure you've noted them somewhere. We're going to use them in a very specific kind of problem right now. But before that, I have a TOK question for you. Is imagination more important than knowledge? This is a kind of a quote. I can't remember who said that. Maybe I should look that up. But it is a quote that's pretty famous out there. The idea, you know what? This might be come from Einstein's quote. His was a little different than that, but he said that same thing because he's considered a very intelligent and knowledgeable person, clearly. But he said that imagination is more important than knowledge. What you know is not as important as how imaginative or creative you are in your thinking, because that's where you can come up with novel ideas and new concepts. What do you think? Please respond. Okay, thank you for responding to that. Let's look at a question now. This is the type of question that's kind of common in the IB world, I have to say, but it kind of just checks your understanding of how definite integrals work. There are four functions or four integrals given here, but we don't know what the function is. We just know there's f of x function and there's a g of x function. So we could not punch that on our calculator because we don't actually have a function. But we're told what the area is from 0 to 2 of that function, or from 2 to 5 of that function, or 0 to 2 of this other function, and 0 to 4 of that same other function. So we're given these integrals and we have to figure these out. Look at a. In a, we have 3 times this function minus this function. Well, by simple rule of integration, we know that that constant can come out like that. We know when we have multiple functions in here separated by plus or minus, we can just take the integrals of each one individually. So just rewriting that in this form. All right, so still 0 to 2, still f of x function here minus the g of x function. But now we know what 0 to 2, what the integral from 0 to 2 of f of x is. We're given it here. And we know what the integral of 0 to 2 of the g of x function is also. It's here. So we have 3 times that number, 3 times 4, minus that number, which is negative 3 right here. And we get a value of 15. Try B in the same way. Do you see a connection between B and these things here? Okay, in B, we have this function, and we know the rule that usually when we do integration, definite integrals, we go from the lower number to the higher number. So that's like if this was the 2 was here and if the 5 was here, we would be saying we want the area from x values of 2 to 5. But they've flipped these around on us. That means we're going backwards. And when we run an integral backwards, it gives us a negative value for the area. So for that one, we put a negative sign in front instead of a plus here, and then we flip this around, because this will now give us a positive value, but we make it negative by doing that, and then it gets back to this. The original one stays the same. However, we know when we run a definite integral and the starting point and the ending point are the same, imagine you have the same x value, you're not actually capturing an area because you're starting and ending at the same place, so you're not creating this zone with an area. So that integral has an area of 0. This one becomes negative 12 because we have the 12 here of f of x 2 to 5, and we have negative 12. All right, C. In C, we have the integral of 0 to 5, and 0 to 5 is not one of the ones we're given here, but we are given 0 to 2 and 2 to 5. So if you want the area from 0 to 5, you can just combine the two areas, right? You can get the area from 0 to 2, combine it with the area from 2 to 5, and you get your total area. So that's what it says here. 0 to 5 of the f of x function is the same as 0 to 2 plus 2 to 5. And then we add those two numbers and get the total area. And D. Okay, in D, we're asked to find the g of x function, definite integral from 0 to 4. So the area under that curve from 0 to 4. To get that one, we can subtract 0 to 2. What's going on there? Oh wait, is that what it has there? 0 to 2. Yeah, okay, sorry. We were looking for 2 to 4, and to get 2 to 4 is the same as saying 0 to 4 minus 0 to 2. Does that make sense? Imagine you had a zone from 0 to 4, and you subtract away the zone 0 to 2, then you're left with the zone 2 to 4, and that's what this one's asking for. And we do know these two numbers, they're one of the numbers, or the two numbers given there, the 6 minus the negative 3, and we get that value there. Okay, I hope you're getting your head around these problems. There's kind of an interesting twist to the concepts we've been talking about. Let's look at E. Okay, in E, we have the half, first of all, can be taken out. So the half jumped out here. And then we have now just f of x. We know, this is important to note, that notice what happened with my boundaries here. When, I think I have a note about that here. There we go. The f of x plus 3, that means by transformations that the function was shifted 3 units left. So this function is 3 units left of the f of x function. So imagine it going 3 units left. That means this thing here goes 3 units left. That means the boundaries change also, right? You shift the whole area thing you're looking at with the boundaries shifts 3 units to the left. So that one, 0, becomes negative 3, and that 2, shifting 3 to the left, becomes negative 1. And that's exactly what we're doing here. We're saying half times this function is the same as, well, half times this function that we have here. So half times 4 is 2. That one's a little tougher, and there's actually a different variation of that we'll look at together in class that's even tougher than that, but let's just start on that one. So now that I've introduced these ideas and you've thought about it a little bit here, let's see if you can try some more just like these. So it'll be just this one last problem set here. See if you can do these. Try A first. And then check your work here. Sorry, it's a little blurry. Wow. Hopefully you can still read that. And now look at B. Okay, so B looks like that. And now try C. In C, very similar to what we saw, we have the 3 to 3, which is the area of 0, and then the 3 to 4 can be turned around backwards. Sorry, the 4 to 3 can be changed to 3 to 4 with a minus sign. All right, how about D? Okay, D, we know that 0 to 6 is the same as 0 to 3 plus 3 to 6, and that therefore 3 to 6 is like 0 to 6 minus 0 to 3. These are very similar to this last one, so I hope these are coming easier for you now. And finally, try E. Okay, E, again, there's a shift. Let's take a look. First of all, you can remove the 3. And then that x minus 2 tells you there was a shift 2 units to the right. So imagine this one is like the g function shifted 2 units to the right. So here's the g function now, and notice the boundaries we've shifted 2 units left because we're taking it back from this one to this one. And we know that value is 10, so we can get that answer there. Okay, great problems. They're kind of logic problems. Hope you were able to completely figure those out. See you soon.